This presentation is about two new connections between the AMPL modeling language and other important software. The first part is about a new direct interface to spreadsheet files. And the second part is about an interface to callbacks from solver programs. And so each one will have some examples to show you how they work. So first, let's start with the spreadsheet interface. Okay. So our new interface can read and write any XLSX file, independent of whatever software spreadsheet software you're using. It works on all popular platforms and does not use any external database drivers, such as our old ODBC interface. Also, this new feature uses the existing AMPL data interface statements, the table statements for associating model parameters to data, and the read and write table statements. So any spreadsheet application using our older interfaces can very easily be updated to this one. I would mention also that we now have a direct file handler for CSV files as well. So here's the example I'm going to give it. It's about a network flow problem in AMPL. And so you see there's a set of products, there's a set of network nodes, a set of arcs, which are pairs of nodes. And the parameters, the capacity parameter is two-dimensional since it's indexed over arcs. This inflow parameter is also two-dimensional, indexed over product and nodes, and the cost is actually three-dimensional, indexed over products, nodes, and arcs. In the AMPL text format for data, the data for a simple example might look like this. You can see various tables for capacity, inflow, and cost. And typically the way we've put it into spreadsheets looks like this. And basically, if it's two-dimensional, there are two key columns in a data column. So you see there's an entry for capacity between Detroit and New York, and one between Denver and Seattle. Similarly for the inflow, and for the cost, because indexed over because it's three-dimensional, it has three key columns in a value. So it's cost of shipping bands from Denver to Boston, cost of shipping coils from Detroit to Seattle, and so forth. So what you see here are actually 5 spreadsheet ranges, each of which gives some of the data that we need. And to get that into AMPL, we just use 5 table statements that give the correspondence between that data and the AMPL sets and parameters that we want to populate. And I've shown here just a few special features. The name of the spreadsheet range can be different from the table name. And here we actually read both the arcs of the network and the capacities from the same table. And once I've set this up, I can just read all the tables, and then I can do a solve. And then I can use more table statements to write output. You see here, I just write the flows, which are the optimal flows in the network. And here I have a more complicated table statement that for each arc writes 2 computed values, the total flow and the percent of capacity used. And when I write these out, I get something like this in my spreadsheet. So you see again, flow of bands from Detroit to Seattle. Here's a 3-dimensional table. Here's a 2-dimensional table. Okay. So there's more, a number of existing more advanced features are also supported by this. So anything that was possible before is still possible. And there are some new spreadsheet specific features, recognizing sheet names, interpreting empty cells. And what I want to mention especially here is that we can now handle 2-dimensional spreadsheet tables, which are very natural in a spreadsheet as opposed to a database. So let's look at this table again. A more natural way to write this in a spreadsheet that people often use is to put the cities on the left and the other cities on the top, like this. So we want to be able to read the table when it looks like that, and similarly for these, okay? Instead of that format that I showed before. And in this new table handler, that's very easy to do. You just add this 2D keyword to these 3 tables, and then they'll recognize that. Okay? And similarly, once you've solved, I can add 2D to this one, and the flows will now be written in a 2D table. So when they're written out, now they look like this. The shipments, the cities are over here, and the products are on the top. That makes working with spreadsheets and reading them a lot more natural. So the second part of the talk, I want to talk about callbacks from solvers. So callbacks are a feature of solvers that enable the solver to periodically call back to the application that invoked it and ask it if it wants to do anything. Okay? And so we've implemented callbacks for AMPL in the APIs, in the programming language interfaces for AMPL, for Python, C++, and C#. And we've implemented generically for different solvers so that you can easily switch from one solver to another. And similarly, there are various generic callback types. And I'm going to show two examples that cover typical uses. One implements a solver stopping criterion that's not one of the standard ones, and the other implements user-generated constraints or cuts. And I'll show the examples in Python, and I'll use Jupyter notebooks. Okay. So the first example is from roll cutting. Okay, and the way this works, that we're given a lot of large rolls, and we want to cut them into smaller rolls according to certain cutting patterns to determine the optimization is determine the number of times to cut each pattern, so that you meet demands for the small rolls and the number of big rolls cut is minimized. Okay? The approach to this is that first you do something to generate many good cutting patterns, such as by solving a lot of subproblems. But what I'm going to concentrate on is the second part, where you have to solve finally an integer program using all the patterns generated. And the idea is that you don't want to spend too much time on this second step. Okay? Sometimes it'll be very fast, but you never know when it might take a lot of time. So you want to apply a solver for a reasonable amount of time and then return the best solution you found so far. And the way I'm going to show that is by using a callback to implement an adaptive stopping rule. And the idea of the adaptive stopping rule is that I have a series of times and a series of tolerances. And when the elapsed time reaches TI, I increase the gap tolerance to GI. Okay, so I relax the tolerance for when to stop. So here's a Python dictionary with a sample rule, and now what I have to do is implement a callback class. And this talk is too short to really go into this in any detail. So I just want to point out that right here is the entire callback routine. This is what gets called back from the solver every time, and test to see if the amount of time taken has exceeded another one of those TIs, and it's time to relax the gap tolerance. And this is another routine, another method of the callback class that just resets the gap tolerance parameter when that is necessary for that. Okay? And this here is all you need to actually run this. And this calls the optimization several times, once after each time that the tolerance has been changed. And but since I have relatively limited time, I won't try to explain everything that's going on here. What I want to say now is that I put all this into a Jupyter notebook, and if I go here, I can show you that notebook. And one thing you'll notice is that the AMPL model is itself in the notebook. So we can put the models into cells in the notebook, just like we put Python programs, and we can then read these, whatever's in this cell, we can read into AMPL. Okay? And this one I've already run, so you can see here, if I go down, eventually here's where all the patterns were generated. And but when I go down here, here's the callback definition that was in my slides. And here's where I run the callbacks. And you can see when I ran them, I got a message increasing gap tolerance to 0.02%, and then increasing gap tolerance to 0.20%. And then finally it found the optimum. And after that, I retrieved the solution and ran a plotting routine and showed the results. And so then let's go back to the I guess that's it. No. Back to this, I don't know why I did that. And so let's go on here to the minimum tour problem. And here I have a set of locations that are connected, and I want to find a subset, a tour having minimum total distance. And there are two kinds of constraints. One say that to be a tour, exactly 2 arcs have to meet at every node. And also to be a tour, it has to look like this and not have subtours like this. Okay, so there are a lot of constraints that eliminate subtours. And the solution strategy is to start only with the adjacency constraints, the ones that say 2 arcs at each node. And then every time you find a feasible solution, you check for subtours and add an elimination constraint for each subtour found. And then you continue with the optimization. So the idea is that there are a great many of these elimination constraints, but you only add the ones that you find out that you need. And the idea is to use a callback to add those constraints. Typically, far fewer elimination constraints will be added than the total number that exist. Okay? So we set up a few parameters here, and we can give any TSP file from TSP Live as the input, and there's a library routine that reads TSP Live files, and we do that, and then I'll skip over here and just say that this here is the callback class, and basically it runs some routine that we wrote that finds subtours, and if there's one subtour, then we don't have to do anything. But if there's more than one subtour, then for each subtour we do some processing and we add a constraint, and that's the amount of detail I want to show there. And then we can then to actually run it, basically this optimizes all we need. We set the callback here and we optimize, and the callbacks automatically are called when they need to be and generate the subtour constraints. So again, I put this into a Jupyter notebook, and so let me get that notebook. There we go. And you see again, the model here is in the cell. Okay? And I've set here the TSP Live file I want to read. And we set everything up, and there are various functions to like plot tours and so forth. And then to look for subtours, and then here's the callback class. And here's the thing that runs the optimization. And so in this case, I'm going to actually run it. And let's see here. It runs quite a bit slower when I'm recording it, but now you can see it's finding subtours. And in each case, you see the subtours it found that's eliminating. It doesn't optimize the subtours, so sometimes they look pretty awful. But it's only the nodes that are in the subtour that really matter. And you see it keeps doing them. And now they're getting fewer and smaller. And there finally it got the optimum. So turned out that we didn't need to set very many. We found, like, I went through 35 iterations of looking for subtours and found relatively few of them compared to the number that actually exist. So now let's see if we can go back to to this. And there's the notebook. And so that concludes the talk. I just want to give credit to the members of the AMPL development team who implemented these two features. And for the spreadsheet interface, you can go to the spreadsheet page, and it's already available for anyone who wants to use it. It hooks into any existing AMPL implementation or AMPL installation. And as for the solver callbacks, we'd be happy to hear from people who'd like to do some testing of it. So thanks for your attention.